Thank you for joining me. I'm going to be looking at a question to do with a car of mass 800 kilograms, and it's going over a speed bump with a radius of 10 meters. So there's this speed bump in the road and it's got a radius of 10 meters, and the car at the top, and there's a person inside. Okay. So we've got the car is mass, we're dealing with a mass of 800 kilograms, and we're going at a velocity of 14.4 kilometers per hour. So let's convert this 14.4 kilometers per hour, 14.4 thousand meters. So now it's turn the 1 kilometer into 1,000 meters, turn an hour into 3,600 seconds, and we can do the calculation 14.4 times 1,000 divided by 3,600, and we get 4 meters per second. So we've got our velocity 4 meters per second. Name all the vertical forces acting on the car when it's at the top of the hump. Well, we've got the gravitational force. So one, we've got F gravitational force, which is mass times acceleration. In this case, it's 800 times 9.8. And so we've got a force of 9.8 times 800. So we've got 7,840 newtons gravitational force. We've got this velocity which gives a centripetal force, and so there's a force in the opposite direction as well, which is the centrifugal force. So we'll put centrifugal force would be mv squared over r. So we've got 800 times our 4 meters per second, so 4 squared over radius of 10. So it's 800 times 16 divided by 10, and we get 1,280 newtons acting up, and therefore they are the two main forces. Now calculate the resultant force acting on this car. So part B, the resultant force would be the difference of our gravitational force, 7,840 newtons, down, take away 1,280 newtons vertically from the centrifugal force acting away from the center, and we've got 7,840, 6,560 newtons acting downwards. After travelling over the hump, the driver remarked to her passenger that she felt lighter as the car moved over the top of the speed hump. Is this possible? Well, yeah, you're sitting in a seat and your mass has this gravitational force down on the seat. So your mass on the seat provides like a normal force onto your body, which stops you from falling through the seat. It gives you just enough force to stay on that seat. But the normal force is reduced because as you go over the speed hump, you don't need as much. That centrifugal force lifts you out of the seat, and the seat doesn't need to provide as much force. So the normal force is reduced as you go over the hump, and so your weight seems onto the seat to be less. So you do feel lighter. You feel lighter because the seat is providing less normal force onto you. If you fly up out of your seat, the seat doesn't need to provide any force whatsoever, at which point you'd be quite weightless. And part D is similar to this question. What is the maximum speed? that this car can have at the top of the hump and still have its wheels in contact. Well, if it goes any faster, the car's going to lift off the road. So what we're dealing with here is a point where your gravitational force matches the normal force of the road on the car. And so at that point, the car seems weightless and it can actually lift off if the force goes too hard, but then it's going to drop back down because we've got we run out of the velocity, sort of disappears because you've got less, the tires aren't going as fast over the road anymore. So we've got them to match the gravitational force with the centrifugal force. So we've got mg acting down is going to equal mv squared over r acting up. So mass of the car is negligible because there's a mass on both sides. So we've got 9.8 is equal to v squared over our radius, which is 10. So 9.8 times 10 is equal to v squared. Therefore, v will be the square root of 98. And we'll just get the calculator to give us the square root of 98. And square root of 98, we get about 7 times 7, about 9.89949 meters per second, and they want that in kilometers per hour. So if you want to change meters per second, you divide by 1,000 meters per kilometer, and you multiply by 3,600 seconds per hour, and we start with 9.89949 meters per second, and then our seconds will cancel. Take that off. We divide by 1,000 meters per kilometer, so we can cancel our meters, and we're left with kilometers per hour. So we times that by 3,600 and divide it by 1,000, and we've got 35.64 kilometers per hour, about 36 kilometers per hour roughly to the nearest kilometer. So I hope this has helped. Until next time, stay happy.